In this video lesson, we're going to look at the periodic trend atomic radius. We'll talk about what factors contribute to atomic radius size and the other periodic trends that we're going to be looking at in class tomorrow. So first of all, in your periodic table, there are a lot of different pieces of information that we can pull from it as long as we learn how to read it properly. It can be like a really, really great cheat sheet. We just have to learn how to pull out the information that's stored in there. So the first periodic trend, which I'm going to use as an example to kind of go through a bunch of things, is atomic radius. So let's start by giving a definition of what atomic radius is. So it's the size, so exactly what you would expect, the size of the atom as defined by the distance between the nucleus and the boundary of where the electrons of that atom spend 90% of their time. So we've kind of learned that an atom has a nucleus, which has positive and neutral charges in the center, and then we have these electrons that kind of whiz around in various energy levels. So energy levels are more like a probability of finding an electron. So a certain area or an orbital is where the electron is most likely to be, but not necessarily where it is. So electrons kind of whiz around all over the place, not necessarily in a specific pattern, but they generally spend a certain amount of time close-ish to the nucleus. So your boundary of where electrons spend 90% of their time is just an idea that, you know, let's say it's within this area. Occasionally the electron might zip out further over here, but mostly they're being found in this electron cloud area. So your atomic radius is the distance between the nucleus and that boundary. In this table are plotted the first 40 elements and their atomic radius in terms of the size. So the first element, is hydrogen, then we've got helium, then lithium. So if we just were to go up, this is by atomic number, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then down here, this last one, we're going to label it as neon. So you're going to work through a very similar kind of activity with the other three periodic trends, but I'll do this one as an example for you here. So label the elements at the peaks of the hills. So we got all the way to neon. This is number 11. Okay, so this is going to be sodium. All the way over here, we're going to get to potassium and rubidium are at the peaks. Then label the last element before the peak. Here we've got helium, neon. This one is argon, and this one is krypton. So I'm just checking to see, this is number 18. So I know that that's argon. It's just by atomic number. So now that we've labeled those, what group of elements have the largest atomic radius? So these four along the top all belong to the group 1 metals, which are called the alkali metals on the periodic table. So they're all these guys. So lithium, sodium, potassium, rubidium. So all this first column. These are the alkali metals or group 1 metals. Then, what group of elements have the smallest atomic radiuses? So now looking at the lowest points, okay, obviously atomic radius in general is smaller when there's fewer elements, but if we were to look at a trend in terms of repeating, the lowest numbers before each peak are all noble gases. So this group that have the smallest atomic radii are the noble gases, which are the last column over at the end here: helium, neon, argon, krypton, xenon, radon, and so on. So E says, how does atomic radius change overall as the atomic radius number, or the atomic number goes up? So atomic number is from 0 to 40 here. So in general, as we see it get to be a larger atomic number, we're seeing a general trend of even these guys that have the smallest, they're going up and up a little bit. These guys go up and up and up a little bit. So we're seeing sort of a general trend in this direction as increasing. So here we can say, generally, as the atomic number increases, okay, the atomic radius also increases. So on the graph, using arrows, show the periodic trend below, the direction for this trend in both like an up and down and side to side kind of way. So what we're seeing here is atomic radius increases as we get more and more energy levels, or more and more atoms in the or subatomic particles in the element. So we get an increase as we go down. So bigger numbers, more shells, more protons, more electrons. It's going to get bigger as we go down. We also saw in terms of side to side that the noble gases were the smallest and the group 1 were the biggest. So the noble gases are over here, the group 1 metals are over here. So it increases in that direction. So overall, okay, as we go from the right to the left, atomic radius increases, and from top to bottom, atomic radius increases. Now, hopefully top to bottom makes a lot of sense. As we go to the next row and the next row and the next row, we're adding shells or energy levels to the actual atom away from the nucleus. So it makes sense that as you add a shell, it's going to get bigger. So more shells equals larger atomic radius. But why across a row does it increase as you go from right to left? It would seem as you add electrons, it should get bigger because you're adding electrons, and so there's just more stuff there, but it actually works in the opposite direction. So atomic radius increases from right to left because of something called effective nuclear charge, and that's what we're going to talk about next. So we'll come back to this in a moment. We'll flip the page over. So atomic radius increases as you increase the number of energy levels. Makes sense. But why does it increase with fewer valence electrons? So that seems a bit counterintuitive. Effective nuclear charge is basically the pull that the valence electrons feel from the nucleus. So we're going to draw a little diagram to sort of help us understand what this means. So effective nuclear charge, we want to remember that, okay, is the nuclear charge as experienced by the valence electrons. Okay, so how strongly do the valence electrons, so the electrons in the outermost shell of an atom, feel the positive charge of the nucleus? So effective nuclear charge, okay, we shorten it to Zeph, or Z effective. Z, if you remember, is the number of protons in an atom. That's what we did with our isotopes lesson as well. So Z, and then effective is for the effective charge of the number of the protons that you have. So that's where that comes from. Okay, the greater the effective nuclear charge, the smaller the atomic radius. Okay, if we were to sort of think about drawing a little diagram here, as the nucleus becomes more and more positive, you're not adding an extra energy level, which means that as it becomes more positive, there's actually a stronger pull on the electrons that are in that valence shell. For this, we're going to kind of use the analogy of going to the movie theater. So in an example of something that has a small effective nuclear charge, so our example is going to be magnesium here. We're going to compare it to something with a larger effective nuclear charge that's in the same sort of circumstance, the same row. So this is going to be example of sulfur. So if you're looking back at your periodic table, we're comparing magnesium here and sulfur here. So they're in the same period, but this atomic radius is larger than this one. So we'll talk about why. Let's imagine for a second that the nucleus is portrayed as a movie screen. So if we're going to the movie theater, okay, here's the TV screen. Okay, and it is playing, a football game or something. And we've got the nucleus, or a movie, an exciting movie. It's representing the nucleus. Now, the seats in rows in front of the television are going to represent the energy levels. So in the first energy level, we have two valence we can have two electrons. Okay, so we're going to put 2 seats in the first row. In the next row, we can have 8 seats, or you can fit 8 electrons in the second energy level. So 1, 2, 3, 4, 5, 6, 7, 8. And for the third row, again, we can fit 8 electrons in that row. So these rows are representing, okay, the energy levels. Now, for the element magnesium, okay, magnesium, if we refer back to our periodic table here, okay, is number 12, which means that it has 12 protons. So the screen will say is size 12. We'll go with that. Okay, we also have 12 electrons. So we'll fill in the electrons. First, we have 2 in the first row. So it's a bit like a Bohr-Rutherford diagram. Okay, we can have 8 in the second row. And then we have 2 in the last row. But because this screen isn't particularly large, so this screen size of 12, these 2 valence electrons, the 2 that are in the outermost shell, aren't as engaged in watching the show because there's so many electrons in front of it. It's almost like it can't see very well. So it's not being attracted to that screen very much, and they kind of tend to wander away a little bit. Okay, so they're not spending as much time close to the nucleus because they're not attracted to that nucleus like a TV screen. It's hard for them to see what's going on. Okay, so not as interested. Okay, so they wander further away. Now we're going to compare that to sulfur. So sulfur, okay, has a TV screen that's larger. Okay, sulfur, if we look back at our little periodic table here, is atomic number 16. So its TV screen, we'll call it size 16. So it's a little bit bigger. It's more exciting to watch. It has the same number of energy levels. So we can put 2 electrons in the first row. We can put 8 in the second row, and we can fit 8 again in the third row. So sulfur's going to have 16 electrons. So there's 10, 1, 2, 3, 4, 5, 6 valence electrons. And though there's more valence electrons here, they're in the same level, okay, as these two, but the TV screen is larger, so they can see it better. There's more of a pull on these guys, all of 6 of them equally, towards that TV screen because it's larger and they're more engaged in what's going on it. So they're leaning in, they're sitting on the edge of their seats, wanting to know what's happening next. They're leaning in, okay, and they're interested. They're inching closer. So they're actually being held closer to the nucleus. They're more interested in the nucleus because there's more positive charge there, even though they're the same distance away, compared with something where there's less positive charge and the same distance away. So we calculate effective nuclear charge, or ZEF, by taking the number of protons and subtracting the number of shielding electrons. So shielding electrons are the ones that are not the valence. Okay, so the ones in front of the valence. So we're going to do an example here with chlorine. So the atom chlorine, we're going to draw a quick Bohr-Rutherford diagram of chlorine to help us understand how to do this. So chlorine has 17 protons and 18 neutrons in the nucleus. It is in the same row on the periodic table as sulfur and magnesium. So it's going to have 3 orbitals, or 3 shells. Okay, and we can put the electrons in. It's got 17. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are all the sort of inside electrons, and those are called the shielding electrons. And then it has its valence electrons, which I'm going to draw a little bit differently. So 1, 2, 3, 4, 5, 6, 7. So the ones that look like this are the valence electrons. So to find the effective nuclear charge for chlorine, we take the total number of protons, which in this case is 17 protons, and we subtract the number of shielding electrons. Shielding electrons are these darker ones that are inside. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So minus 10 equals 7. So the effective nuclear charge for chlorine is 7. Now you might notice that 7 corresponds to the same as the number of valence electrons, okay? And that's something that you're going to see as a bit of a pattern, okay? The number of valence electrons, okay, is equal to the same number as the ZEF. Even though they're the same number, they don't mean the same thing, but they're the same number. So we're going to practice. What I'd like you to do is pause the video and give it a try. So you're going to practice calculating the effective nuclear charge for these 3 elements, okay? Then you're going to see if there's a pattern. Then you're going to try those 3 and see if there's a pattern. So pause the video for a second, give it a try, and then play it again. So hopefully you gave it a bit of a shot. Sodium, okay, has 11 protons minus 10 shielding electrons, gives us an effective nuclear charge of 1. Potassium has 19 protons minus 18 valence electrons, which gives us an effective nuclear charge of 1. For cesium, we've got 55 protons, 54 shielding, gives us a total of 1. So what do you notice about the ZEF of elements in the same family? It's the same. For aluminum has 13 protons minus 10 shielding electrons, gives us 3 for the effective nuclear charge. Oxygen has 8 valence electrons minus 2 shielding electrons, gives us 6. Argon has 18 protons, 10 shielding electrons, which gives us a total of 8. So what do you notice about the Zeph as you move from left to right on the periodic table? So left to right, it increases. Okay, just like the valence electrons number increases as you go from left to right across a row in the periodic table. So why do we care about this? Let's quickly make a summary note on this front page. So we learned earlier that as you add more shells, you increase the atomic radius. Okay, and if you increase the effective nuclear charge, okay, that also is going to decrease the atomic radius. So increase effective nuclear charge, decreases atomic radius. To kind of have it match up with this arrow, we can even rewrite it as increased atomic radius equal to less Zeph. Might be better to write it that way, seeing as we're talking about increasing atomic radius. Okay, so when comparing two elements, okay, we might be looking to see, okay, between aluminum and chlorine, which one do you think is going to have a larger atomic radius, and how are you going to prove that? Okay, and the way we do that is using what we call the SIR method. So claim, evidence, and reasoning. And you're going to go through these steps to be able to express how this works and how you can kind of prove your point as to which one you think is going to be smaller or larger. So in this case, if we're comparing aluminum and chlorine, the evidence step is first. And we need to show 2 lines of evidence. So firstly, we need to calculate the Zeph for both aluminum and chlorine. Then we have to talk about the number of shells, because we know that those are the 2 things that are going to affect our determination of atomic radius. So here, aluminum, to calculate Zeph, we take 13 protons minus 10 shielding electrons, gives us a Zeph of 3. Chlorine has 17 protons minus 10 shielding electrons, gives us a Zeph of 7. If we compare the number of shells, okay, aluminum has 3 shells. It's in the 3rd row, so 3 energy levels. And chlorine is in the same row, so chlorine also has 3 shells. So once we have our evidence, we can reason through and explain in sentences what this means. So here, aluminum and chlorine have the same number of shells or energy levels. Therefore, the only difference is the effective nuclear charge, or Zeph. Chlorine has a larger effective nuclear charge, meaning, I'm gonna have to move this claim down a little bit, meaning it holds its valence electrons closer, giving it a smaller atomic radius. Okay, and if we finish this off with a claim, we want to make sure specifically that our claim matches the question. So in this example, it was asking for which one is larger. So my claim would be a final statement saying aluminum has a larger atomic radius. And that's where we'll end things. We'll do some practice of this in class.